resource papers as well that I think looks very interesting and also in use. So we've got a nice spread across the story in this session this morning. My name's Kerry Taylor. I'm from the Australian National University. It's my pleasure to share this session. And more than that, I'd really like to introduce here Jiashang Huang, who is from Nanjing University in China. And Jiashang is going to speak to the topic TransEdge, Translating Relation Contextualized Embeddings for Knowledge Graphs. And this is a reframing of how you put your graph into the knowledge graph, into the embedding representation by focusing on the vertices as opposed to focusing on the nodes on each end. Is that a fair enough description of it? Please take it away. Are we on here? Thank you, Jiashang.
Okay.
Oh, that's correct.
Okay. It works. Hello, everyone. Today I will introduce our research paper, TransEdge, Translating Relation Contextualized Embedding for Knowledge Graphs. First, I will introduce the background and the motivation for our work. A knowledge graph is a multi-relation graph whose nodes denote entities, and direct edges are associated with types indicating the specific relation between entities. For each edge in the knowledge graph denotes a relational triple which represents a fact. For example, this edge in the knowledge graph represents the fact that the movie From Dusk Till Dawn has a director whose name is Robert Rodriguez. Formally, a knowledge graph can be defined as a triple in this form, where E is a set of entities, and R is a set of relations, and T is a set of the triples. Now we will discuss the knowledge graph embeddings. Knowledge graph embedding techniques seek to encode entities and the relationships into vector space and capture the semantics by the geometry structure of the embeddings. In this paper, we focus on the translation KG embedding models. The most popular KG embedding models is the TransE. In the TransE, for a relation triple HRT, we use it uses the vectors of H and R are connected by a transformation vector of R. That is to say, when H plus R is approximately equals to T. The TransE uses the energy function in this form to denote the errors in the model. It also uses the energy function to train the embeddings for the entities. Here, this figure is an example for the embedding of these triples. Here, these 2 points are the vectors for these two entities, and here is this vector is the translation vector. It is the embedding for the relation located in. Knowledge graph embeddings have many applications, such as link prediction and entity alignment. We will discuss this task later. These translational models use transformation vectors as relationships. These models cannot model the complex relation structure of KGs. Here we consider the example in the small knowledge graph. When one entity pair has multiple relations, for example, this entity pair has two relations, director and editing. Here, the TransE will use similar relation embeddings for these two relations. And when the multiple entity pairs has only one relation, then the embedding for the two entities are very similar. If we use these similar embeddings to do inference, it may cause errors. For example, if we want to predict the writer of this movie, it may use output Church Marine as the output. However, it's not true because we can see that Church Marine is starring in this movie. To address this problem, the existing translational models are transformed the original embedding for the entity to a linear subspace. Here we take TransH as an example. It is use the projection transformation as G1R and G2R. Here it projects H and T is the original embedding for the entities. It projects H and T to a hyperplane of R here the translation vector from HR to TR is the embedding for the relation. Here we can see it is possible to model multiple entities with the same relation. However, these tail entities are lies in this line, so these entities are much similar to each other. So these models also cannot address this problem thoroughly. Here we will see our approach, TransEdge. This figure is the graph structure of the KG. Here we can see that for entities, it has explicit embeddings. That is to say, for each entity, it has a fixed point in the vector space. As we can see, now we will consider the edges in the knowledge graphs. In the TransEdge, we introduce the edge embeddings. That is to say, the translation vector from the entity pair is the embedding for the edge rather than the relationship. Based on this formulation, we can see that these two edge embeddings are same. However, they can encode the different information from different relationships. And these two edge embeddings are different. However, they use the same relation labels. Now we will give the details of our model, TransEdge. Here is this figure gives generalized information of our model. In this figure, these two blue boxes are general entity embedding for head and tail entities. And this yellow box is the edge embedding for this triple. Here we use the function phi to combine the head entity and tail entity and the relation embedding together. Formally, the energy function of our model can written as this. We call the function phi is the contextualization operation. It generates edge embeddings. Here, for each entities, we have two embeddings. First is H and T. It is the general embedding for entities. It is capture the geometry positions and the relation semantics. And HC are interaction embeddings for entity H and T. It is used to generate the edge embeddings. Here is our parametric complexity of our model. In this paper, we designed two contextualization operators. It is the first one. We call it context compression. It is used multiple layer of perceptions to compute the embeddings of the edge directions and the labels. Since it uses three vectors as input and output only one edge embedding, so we call it compression. We first combine the head entity and relation together, and then combine the relation and tail entity together, and sum up these two relationships and use MLP to obtain the edge embeddings. Here we use different MLP for these two parts because when we interchange the head and tail entities, the edge vector should be different. The second approach is similar to TransEdge. However, we project the relation to the context created by the entities. For example, in this figure, H and T1 is an entity pair, and it creates the contexture like this hyperplane, and then we use the projection function to project R to the R double prime. We use MLP to obtain the projection vectors. And we also required the projection vectors is a unique vector, so we can use this simple formula to obtain the vector of the edge. This is the loss function of our model. We use the conventional marginal ranking loss. It is similar to TransE. Here T is the positive triple set, and T minus is the negative triple set. We use negative sampling to obtain this set. And we minimize this loss function. So for positive triples, we hope its score function is smaller than gamma 1. And for negative triples, its score energy function should be larger than gamma 2. We deployed our approach to two different tasks. First is interalignment. Here is a real-world object. However, it has different URI in different knowledge base. So the interalignment is to find the entities in the different KGs, which is referred to the same real-world identity. To fulfill this, to tackle this problem, we minimize this loss function. Here, L is the previous triple loss function, and this is for the interalignment. Here, in each step of training, we first select a set of entity pair, it's the entities which are likely to be alignment. Here, we hope these entity pairs. I hope these entity pairs are similar, so its distance should be minimized. Another task is link prediction. For example, here we don't know the head entity of this triple. That is to see if the link prediction model can predict the entity should be the validant. Here we also minimize the loss function of the triples. It is similar to trans-E. Then we conduct experiments for our model. First experiment is for interalignment. We use conventional DVP and DWY dataset. And the computators consist of existing embedding-based interalignment models. And we also combine existing embedding models with our EA loss functions. We also use the conventional metrics to evaluate the performance. As we can see from this table, Trans-Age CP always obtains the best performance. In addition, we find that if we use the semi-superposition, it always improves the performance. For example, is here. On the DWY dataset, we found that Trans-Age CC and CP sometimes obtains the best performance. Sometimes Trans-Age CC is better than CP. However, this difference is very small. Here is only about 1.2%. Then we conduct experiments on link prediction. We use the conventional datasets, these two datasets, and we compare with the most existing knowledge graph embedding models. We also use these metrics to evaluate the performance. As we can see, Trans-Age CP can achieve the best hits at once among all these models. And in another metric, rotated E may be much better. We also further analyze the embedding whether Trans-Age can model complex structures. First, we consider one entity pair with multiple relations. We synthesize a KG with double relations. That is to say, for a triple HRT in the original knowledge graph, we create dummy triples HR prime T, where R prime is not a relation in the original knowledge graph. So the new knowledge graph have the same semantic knowledges to the original knowledge graph. However, the structure is much complex. As we can see in this table, the performance of M trans E is significantly dropped, especially in here, and it's very apparent. However, the Trans-Age shows less variation than M trans E. It shows that our model can tackle very complex relation structures. Here is a visualization of our model and M trans E. Here we can see that translational vectors in the M trans E are also parallel. So, however, our model produces flexible and robust embeddings. We also compared with conventional interalignments. We combine log map also use attributes, so it produces better score, and the combination always gets the best performance. In this paper, we propose a novel translational model with translating the edge embeddings rather than the relational embeddings. And it achieves a state-of-the-art performance on both interalignment and link prediction. Thank you for your time. We also released our code on the GitHub repository. You can check out it.
Thank you so much. Do we have any questions? Please.
Thank you for your talk. Actually, I just would like to know if, regarding your task of anti-alignment, have you tried with, because we have in this conference also a workshop on ontology matching, and there are some standard datasets. Have you tried your trans-edge on these datasets and see what is provided? I have seen that you have compared with Bloodman, for instance.
Compare with this?
The ontology matching community has a lot of standard data sets, so it's entity resolution specifically asking whether you've tried it with those.
We didn't compare with this existing ontology matching because, for example, in the OAEI data sets, there are very little relationships in the data set. It is have lot of attributes in the knowledge graph. So it is better to use the conventional interalignment approaches.
So, with that, is there another question? Okay, thank you very much for your talk. It's very interesting improvement on the other methods. Good to see. For our next talk, could the speaker come up? Here he is. So our next talk will be a resources talk from Mehdi Ali, who's from the University of Bonn in Germany. Mehdi is going to talk to us about a package of things called the King Universe, and there's a zoo in there somewhere as well, yeah. Which is very nice tooling package in order for the knowledge graph embedding community be able to reproduce results and publish and reproduce results in the models that they build in a reproducible way so that other people can pick them up. So I'm very interested to hear about this, man. Are you right to go? Just a minute, I'll need to do... You are. No, you're not.
May I use yours?
Yes, of course. I don't know why I can't see you. I have no idea what that is, but it's not that. Oh, yes, it is you.
This way. This doesn't work, but it's not a problem.
Okay.
Yeah. Okay, welcome everybody. So, it's the best way to start like this. So I will present our work called the King Universe, an ecosystem for knowledge graph embeddings with a focus on reproducibility and transferability. In the beginning, I will give a short introduction about our work and speak about the foundations. Then in the main part, I will speak about the methodology for our ecosystem, where we focused on two aspects. First, reproducibility, and second, transferability. Then we show some applications. in specific the prediction of crosstalks and hierarchies between biological pathways. And then I show how we evaluated our ecosystem, and at the end we give a short discussion and talk about our future work. So everybody knows what a knowledge graph is, but just to recap, so we consider a knowledge graph as a multi-relational graph where the nodes represent entities and the edges represent relations between them. Usually these knowledge graphs are incomplete, and there has been proposed different approaches how to derive missing links, such as rule-based systems. And a new kind of approach which got a lot of attention in the recent years are knowledge graph embeddings. And the idea of knowledge graph embeddings is to encode the entities and the relations of knowledge graph in a low-dimensional feature space. In this example, in a two-dimensional space. They are called latent features because the features that we learn for each entity and relation are not directly observable in the data set. So since the first models has been proposed, now we have a big set of models, but one of our motivations for this work was reproducibility of this model is not that easy. So as a first example, you can see on the table left, this is the model trans-E. We can see on the right column, 3 base 15 Ks. So it got a result of 47.1. And some years later, a new paper was proposed. Same data set, same model, trans-E, the second table on the right, first row. We suddenly see we have an increase of performance about almost 20%. And the question is, how these performance discrepancies, what are the reasons for these discrepancies? There's several reasons. For example, different hyperparameter values, different training approaches, but it's not obvious, and they are not properly discussed in the literature. And these are just one of those examples, and we can find many of these. Same model, for example, for trans-H. This column here, we can see in the original paper, trans-H performs better than trans-E because it was an extension. But here again, this paper in the right table, trans-H performs even less than trans-E. The second motivation was, okay, knowledge graphs are not only relevant for the semantic web community, they are used in different kinds of communities, such as life sciences, scholarly metadata research, and there's a high potential that these kinds of approaches can be used for their applications. But to apply those models for different communities which are not experts in this method, specific aspects must be taken into account. So we formulated two research questions. First, what methodology is required to make knowledge graph embedding research more reproducible, and what methodology is required to make knowledge graph embedding research transferable to other domains? So now we want to speak about the methodology that we have developed. So we defined several requirements for our ecosystem. First of all, we need transparent experimental setup. That means the user needs to have the possibility to have a full control about the experimental setups. The training procedures must be equal for all models, and they must be transparent. And the same is also valid for the evaluation procedure. Second, then we need an ecosystem which is comprehensive. We cannot have just two models and then say, okay, we want to reproduce just these two models and apply it for different domains, because different domains have different problems, so that different models should be taken into account. So we already need a set of models. And this is relevant for reproducibility and transferability. So it's here. Then if you want to transfer knowledge graph embedding research to other domains, it is really important that we address experts and unexperienced users, because we cannot expect that each of the users has a deep programming knowledge or deep machine learning knowledge. So this we should also take into account. Furthermore, if you want to make the research transferable, we should also take into account the requirements of these domains and see how we can specialize general solution for their needs. So then let's talk about reproducibility. So to do this, we had developed Python. This is the main package of our ecosystem, which is responsible for training and evaluating knowledge graph embeddings. The input is a knowledge graph, and the output are then the learned embeddings, the trained model, and the configuration describing the whole experimental setup. The architecture has two layers, a configuration layer and a learning layer. In the configuration layer, the user can choose the model that he wants to use and has a full control of the experimental setup. In the current version, we have already 10 models implemented. So we are already comprehensive, but we will extend it in future. And through the configuration layer, we provide the users with the full control of the experimental setup, which was one of our requirements of our ecosystem. So then in the learning layer, we can train a knowledge graph embedding model in two modes, one in a training mode and one in a hyperparameter optimization mode. So training mode, if you know which hyperparameters to use, then go ahead, select them, train, evaluate it. But often it is the case, especially in other domains, for researchers from other domains, they don't know the specific hyperparameter values. So we provide a hyperparameter optimization so that the ecosystem automatically then detects the best combination of model and hyperparameters for a specific problem. So in our learning layer, we provide transparent training and same evaluation procedure for all the models. So we have a fair comparison of the models. And then in general, our first requirement to have a transparent experimental setup is met. And the same is also for the comprehensiveness. So the goal is not to have just a framework which we have a paper now and now the work is stopped. So we want that is also driven by the community. So for this reason, the software architecture must have specific aspects in the architecture. So we said we want to have a very modular architecture, so it's easy to extend with new components. And our central component is the so-called pipeline, which manages the whole workflow, which interacts with the different submodules. For each new knowledge graph embedding model, we have a KGE module that needs to be extended. If you want to provide new hyperparameter optimizers, we have specific modules also for this. And since we already have a set of implementation for each of the modules, it's quite easy to integrate new ones based on the existing ones. So important also for reproducibility is also, that we can share our experimental setup. So we have also created a model zoo. And the idea is, okay, if we have published a paper, that we can, in our model zoo, we can publish all the experimental artifacts and the data set, and to easily share it with the community. So we uploaded, for example, one of our the experimental artifacts of one of our works, and you can see that we have specific requirements. So we expect the users to provide all the configuration files. We want the links to the resources. So most important that the data set is open resource, so the results can be also reproduced. And it should be a work that is published. So we have also a quality. We ensure a specific quality of the work. Now we want to speak about transferability. How can we extend Python for the use in different domains? And we, as one example, we target the biomedical domain because their knowledge graphs de facto standard to represent biological findings. And what was important here, we have to see, okay, what are the aspects of the users? Probably a typical bioinformatician is not an expert in knowledge graph embedding models, and he's probably also not an expert in programming. So in PyKeen and in BioKeen, so BioKeen is an extension of PyKeen, how we can see here. So the learning layer is done by PyKeen, but we have provided interactive command line interface, so all the experiments can be configured through a terminal, so you don't need any programming knowledge to run and evaluate knowledge graph embedding models. As a second aspect, what we did, we implemented a data acquisition layer. So we integrate different data sources, like Index, Bio2Bell. Index, for example, is an online commons where biologists can upload their biological network, and each biological network has an ID. And just by providing the ID to our software, we will download and convert it in the internal format so that it can be processed. So also here, no time needs to be spent for pre-processing. It's done automatically. Yeah, and then you can use the whole advantage of PyKeen that I described previously, learning and also performing hyperparameter optimization. So we address expert and unexperienced users with BioKeen, and we showed how we can specialize PyKeen for the purpose of other domains, such as in life sciences. So in our data acquisition layer in BioKeen, which BioKeen is the second part, component of our Keen universe, I forgot to mention this. So PyKeen is the general machine learning framework. BioKeen is the extension of it, which was designed for the biomedical domain. And these are some of the data bases that are directly accessible through BioKeen. So we have different kinds of knowledge graphs, for example, pathway interaction, drug targets, protein pathway. So this can be directly accessed through our software. Now I want to present one specific application. So that's a prediction of crosstalks and hierarchies between biological pathways. So biological pathways represent biological processes which consist of a set of genes which together are responsible for this specific process. For example, here we have the glucose metabolism process, which contains a set of genes. And now in this data set, which is called pathway, it contains relationship between pathways. So this is a specific pathway which is represented by one of the nodes in our data set. And we want to describe relationship between the pathway. Specifically, we want to describe equivalences between pathway, which pathways are equivalent, and hierarchies of pathway, which pathway is part of another pathway. So what we did, we used our software. So ComPath is directly accessible in BioKeen, so we didn't need to download to pre-process it. Then we performed the hyperparameter optimization based on 5 models. And the best performing was TransE. This can have different reasons, which can be also addressed later in the QA session. But what we want to highlight here, so TransE, we have 2 results. So 19.1 was the original hyperparameter setting that was proposed by the authors of TransE for the data set FreeBase15K. If we use this hyperparameter setting, we will get really poor results. But when applying the hyperparameter optimization that we propose with our software, we can get a big improvement. And then we used the best model to predict new links. And interestingly, we found 2 novel links, which then were afterwards added to the data set. So how we evaluated our ecosystem? So we focus on the usability. So usability is defined as the extent to which a software system can be used to achieve a goal of effectiveness, efficiency, and satisfaction. In our paper, we described 2 specific use cases. But here in general, we want to show there has been already a set of works which used our ecosystem successfully. Okay, I presented, for example, the prediction of novel crosstalks between biological pathways. We were also protein-protein interactions. We had also provide co-author recommendation. Recently, it was also recommended in a review about biomedical data science, and it was also used by a company, by Bayer Crop Science, where they have a knowledge graph describing field trial experiments. Discussion and future work. So we have shown our methodology, how we developed our ecosystem so that we can address 1, reproducibility, and 2, transferability. Our ecosystem currently consists of 3 components, PyKeen, BioKeen, and the Keen Model Zoo. We presented real-world applications, how our ecosystem can be used. And in future, we want to provide a methodology to make suggestions what kind of models to use for a specific use case. Because often a user doesn't know which model to select from the, let's say, from the set of 50 existing models. So there we want to help the users. We want to add more machine learning models, and we want to perform benchmarking. And one thing that we want to mention, PyKeen 1.0 is coming soon, in the next couple of weeks. So we have big improvements, added new models, new training approaches. So then please check out our GitHub repository. Thank you. Yeah.
You were first, yeah. Thanks for the talk. I was wondering, how do you implement the embedding models by yourself or by reuse the source code from the original?
Yeah. So what we did, we implemented all by ourselves. So we want to have it integrated in one framework, so we have a fair comparison. So for sure, we first looked at the original code, whether it's available or not, then to see to have a correct implementation. But we implement them by ourselves because it was important that we have it in a unified framework.
How about the goal of the implementation to just try to close to the result reported in the literature, or if you get better results, you trust more about your implementation?
Yeah, so there are two aspects. One is first to try to reproduce, which is currently a major issue because of different reasons. And with providing such a framework, we hope that when providing new model, that the authors of the paper directly integrate their model in the framework, then it's easily to reproduce. And secondly, it would be also nice to investigate why, for the same set of models on the same data set, why these discrepancies came. So we would also try different hyperparameters, and if we get better results, we want to investigate what are the reasons for this. Yeah.
What I wanted to ask you, which is, are other people actually putting their models in your framework?
Please.
So who is putting their models within your framework, or so far it's just the team that's done that?
Yeah, so in Wien it was just a team, but we easily got extended. Now also we're now 6 to 7 contributors, which liked it. And in PyKeen 1.0, then there's the bigger team involved.
That's where you
Yeah.
Good to know.
Yeah.
Yes.
Are there any more implementations of this kind where they've implemented lots of graph embedding approaches and released it? And I can understand there might be academic and I understand you from accounting, so it'll be better to you could extend that. But are there more, and do you link to other such approaches that you know of?
Yeah, so there are also other existing frameworks. So your question is whether we link also to other implementations which are already existing, right? Yeah. So yeah, for example, in our source code, we also link to other implementations. So if we have an implementing specific model, please check out also here this side. They have also implemented this, also been done. Yeah.
So we've probably got time for one more question.
Okay.
Ready?
Yeah.
No? Thanks so much.
Yeah, thanks.
Sit up. So our final talk in this session is an use-track paper, and the topic is knowledge graph embedding for eco-toxicological effect detection. Our speaker is actually from the water resource in Oslo, in Norway. So there's a wide area, which is nice to hear about, especially in Newstrack. That's why it's Can you stay at the end to show you the copy of the presentation? Just don't run away.
Yeah.
Okay, so Eric, you kind of ready to go? Let's
Yeah,
check
sure.
this way. Terrific, over to you.
Yeah, thank you. Yes, so I'm Eric. I'm a PhD student at the Norwegian Institute for Water Research. And today I'm presenting the in-use case for the effect prediction in the Norwegian Institute for Water Research. So, a bit of context. There are millions of chemicals that can affect the environment and the species living in the environment. And we can make an assessment of this, of the risk to this environment, but this requires a high degree of reference data. So in this project, in this in-use paper, we try to mitigate some of the problems with this, with the use of test organisms and also experimental effort, i.e. money. So we'll look a bit further into the ecological risk assessment, where this work is supposed to be used. So you can have an exposure to a chemical in the environment, for example, in a lake, and then we have the reference effects data, which we then combine into so-called risk quotients. Here it's a simple fraction, but it's more complicated in real life. And this is obviously restricted by the effects. And then we can calculate some risk for the group of species. It can be just a single species, or it can be all the species living in an ecosystem. And then we can identify further species that may be susceptible to these chemicals. And then also describe how and which chemicals affect the species, the organisms, which again can be put to the or given to the laboratory as a new hypothesis for the for testing. And then to mitigate this, we have created a knowledge graph embedding approach, and therefore we need a knowledge graph, which has multiple benefits, obviously. But, so to gather this effects data, we use the US Environmental Protection Agency's Ecological database, and to gather some species data, which we need to make predictions, we use the NCBI taxonomy. And then finally, to gather chemical classifications and features, we use the Chembol database and the PubChem database. And then the Ecotox database uses proprietary chemical identifiers, so therefore we need to align them to the chemical data we gather. We do this through Wikidata. We're lucky enough that Wikidata has this alignment. And then the effects also need to be aligned with the species database, which we use LogMap for, which gave us a recall of about 100 on the few test cases we were able to gather from the literature. Okay, so we're moving on to our effect prediction problem. So let's say we have a set of chemicals and a set of species, and these each have their own hierarchies, totally separate. And then we can have positive samples in the experiment, so a species or a chemical affects a species in some way. And then we have some negative samples where the given concentration in the experiment did not give any effects to the species. And then, or here we limit ourselves to binary classification because that's just the stage we're at this moment in time. So to solve this problem, we have developed 3 models, and the first is based on some taxonomic distance. So for example, we want to figure out this: does the chemical 3 affect species 3? And then we can find the closest species which has data attached to it, which is species 2. And then we figure out that, yes, it affects species 3. This is a very simple model, but it's one that's proposed to be used by researchers at the Norwegian Institute for Water Research. And then we go further and introduce a multilayer perceptron model, which just uses one-hot encodings as inputs, passed through a dense layer, and then concatenated and passed through a series of dense layers before we get our prediction. And then finally, our knowledge graph embedding models replaces the input to this model with the chemical classification and the species taxonomy. We have used in this work 3 different models, which were chosen because they're widely used in the literature and have shown good results. And then one final thing is that we optimize the embeddings at the same time as we optimize the prediction model. This is sort of to squeeze the embeddings or push them in the direction to be optimized for the task at hand. So, we can look at some results. The baseline model, which is a taxonomic difference, gives us very high recall, but lacks in precision, which is not great, but one thing I forgot to mention is that we do favor recall because we want to protect the environment. So false positives are not that necessarily bad. But we don't want to give the laboratory all the possible combinations of chemicals to test. So introducing the multi-layer perceptron model yields a much better balance between precision and recall. And then we can introduce our knowledge graph embedding input layers, which yields us a better recall and better F2 score. And we can even improve since we want to improve our F2 score, we can actually reduce the decision threshold to 0.3 to yield quite good results compared to the multi-layer perceptron and the baseline model. So, summary, this is quite quick, this talk, but that's fine. Summary, fine. It's good. Okay, so one of the benefits of creating a knowledge graph, not just for the prediction, is obviously improved data access for researchers in the field. So we have shown that this introduction of knowledge graphs improves for binary predictions. And the next pieces of research to continue in is expanding the knowledge graph with all relevant data such as habitats or rules generated by domain researchers. Also explore the use of more sophisticated model. As the talks we've seen before, we can definitely need to use more other types of models. And then obviously, because we want to predict concentrations in the future, we would move, or we would like to use this obviously in the risk assessment pipeline, and therefore we need to predict chemical concentrations. So, and the resources are available on GitHub, so just go download it, and then come and visit us at poster 466. Thank you.
We have a bit of time for questions. Please.
So thank you for the talk. The negative samples,
Yes.
Are they known to be negative? Is it a certain close?
Yeah, so in the data it's presented as no effect concentration. So at the concentration they tested in the experiment, they observed no effect.
Oh, so it's really a fact. It's not.
Yeah, it's a fact. Yeah, but obviously the concentrations, the higher the concentration, the more likely an effect will occur anyway. So they could have just tested on a low concentration.
And how balanced are the data?
It's about 60% positive for the negative.
Yes, please.
Can you say a little bit more about the actual use of this? I mean, in terms of transportation of their actual users?
So the research institute does a lot of work for governments or local and global for assessing risks for a lot of ecosystems. So the final, obviously, this is early stages in my PhD and also for this project. But this data should be, or these predictions would improve this risk assessment and therefore can improve our understanding of how different chemicals can affect the ecosystem. Is that copy?
Some interesting ideas for some work we have going on in risk assessment, similar sort of environment to what you're talking about. That was part of the
You said it has 60% effects, right?
Yeah. Yes, so that we set, obviously, if you set no upper limit to the search range of the baseline, it will find everything. But we set some upper limit so that it doesn't, because if you don't set an upper limit, you will get recall 1, because you will find everything, right? But we need to limit the search range. We can talk about it later at the poster, if you want to.
Is there another question?
Yes.
Would you consider including information about the ecosystem or the medium where the species live?
Yes. Yes. So in our work, we work mostly with in water, but obviously freshwater and saltwater, there are quite different conditions for chemicals. So especially for the chemical side, they are affected, or they're changed molecularly based on in which sort of environment they're in, which is very important.
And the temperature will make a big difference.
Temperature, pH, everything will make it a big difference. So this is future work. Yeah.
Do we have other questions? I'll just make an observation tying in what I saw in this session from what we had this morning. It's interesting to me that, I don't know, are we going down a path with knowledge graph embeddings which may be not the right way that we as semantic web people should be thinking? We had that talk this morning from Dougal about representing stuff in a nice conceptual model. So the relational database story, it's a nice conceptual model, and then you do the logical, and then you do the physical, and then you get lost and you can't round trip it and it takes 2 days. Are we kind of heading down that path again? Because we've got this nice semantic representation, and then we turn it into all these matrices with all these numbers there and put it through all these nodes and networks, these network nodes that all do something we don't quite know, and something pops out the other end. It's just a little question to ponder over, or whether we could be doing more work on bringing what does work with these models, and there's no question, and we've seen it here, they work well at traditional problems even that we've done in more semantic ways before. Can we bring the benefit of those techniques back more without changing the data into a different representation, but bring the benefits of the methods that work back into the semantic world? It's just a question to ponder that I've been pondering over this morning. Make it more native to and then you get potentially like explainability and connectability between what we're doing. Anyone want to argue with me? You're about to tell me. You've already done this.
A follow-up question based on what you mentioned is probably explainability is a
Yes.
very important factor.
Yeah.
We are investigating it, yeah.
So obviously the embeddings approach is not very strong.
No. Yeah.
So I think this approach is right.
Yeah, the baseline obviously is very explainable, but we're investigating methods to try to explain the embeddings. Yes, but I haven't seen much work on it. So
And it's a good point. In your environment, you have to defend it.
yes.
Yeah. Any other comment? Anyone agree with me? We should be doing more. I think I've got a nod over there. Thanks for that. Okay, thanks so much. We get to access to the coffee while it's 2 o'clock and the food before the bits go.
Yeah.
Thank you so much for coming to the session. Thank you.